Talk about today is that in Micatu, we did an extensive survey using Z prime of really what are some of the challenges, what are some of the technical challenges that we have to solve as we move more into what I'd like to call circular topology. Before I get started here, the old traditional way of a linear topology from your power generation, from your transmission to your substations, to your distribution to your end users is really fundamentally being disrupted. And we really wanted to get a breadth of information from utilities. So we conducted an extensive survey using Z prime. We found some interesting facts that we'll present today. But the one thing that was really staggering is 90% of utilities will have integrated renewable energies within the next 5 years. So we did this survey in 2001. So, and then by 2026, we're really going to be in a point where this is going to provide a lot of opportunities for technical challenges, but a lot of challenges that could actually have impact power quality in our daily lives of how we consume power. If you really look at what is the impact renewable energy is, a part of the survey that we took, we found that 68% of utilities are not satisfied with the quality of the data they're using to manage the grid. Now, this is an important statistic as you think as we change our topology and we really see the rise of what I like to call the prosumer is, data is the new currency for management and control. Really, the grid of the future we're talking about is where consumption and generation can be actually localized down to a house level. We're starting to see more and more of that. While demand of renewable energy can be intermittent, we have to also be able to tie that back into, rotating mass. And as you guys were talking about, Brad, earlier, Brad and I have had many conversations about this, of the rotating mass inertia tied into renewable energies. The other interesting fact we found is 64% of utilities say the power quality is a top challenge. So as we put more renewable energies on the grid, we're finding that the DC to AC conversion is a challenge, particularly around harmonics, frequency imbalances, and the failure of equipment can really put a lot of damage on there. But to address a lot of this is what we have to do is we have got to have more advanced monitoring. Now, monitoring may come in the form of sensing, it may come in the form of actual meters at end users, but there's many different forms of monitoring, and this is all part of the challenge as we integrate into this new grid. If you really think about what does this cost us and what does this impact, right? Is that the survey that we found is it's 180 billion annually cost of poor power quality. And this can be anywhere from asset failures to lack of power, to factory shutting down, to loss of businesses and their ability to operate. It's a big problem, and it's only going to get worse as we put more renewable energy and as we circle into this circular topology. One of the interesting things is a lot of this change is not only mandated by different governmental and state, local, and federal, but it's also going to be a part of the consumer's demand for cleaner energy, right? This is really costly because if you think a lot of our substations, in addition to this, are over 60 years old with their equipment and their structure. And with a lack of parts and other infrastructure items, this is really a problem that we need to start to face. And I think utilities are becoming more and more aware of this. And as technology and innovators, it's really part of our job and our thought process is like, how can we fill these gaps? Because this is a serious issue that we need to make sure that we are on top of. You don't want to be behind the 8 ball on some of the issues that we're talking about. So going into current commercial grade metering, it's costly. Part of the thing that we need to think about is when we're co-generating, when we're adding power to the grid, when we actually, if you are a large industrial complex that actually has a large renewable deployment on your complex, is that metering from both the consumer and generator side to the utility side is important. So this is part of the problem we also have to face is now we have cogeneration and commercial metering grade is becoming more and more important. More sensors are required as people, as the prosumer, actually want to get paid back for the energy that they're not consuming, placing back on the grid. And I'm going to talk a lot about harmonics. Harmonics are actually very important. Harmonics, both the voltage and current side, are good indicators of the grid health. particularly around inverters, particularly around transformers. This can really cause a lot of havoc. Current sensing technologies are lacking in harmonics. And this is why we, as Micatu, have focused on optical sensing, because it gives us not only a greater depth of precision and accuracy, it gives us a larger pool of data to help manage this topology that's rapidly developing. I think one of the last things too is that real-time data is now becoming critical. The cloud has always been sensor, device, IoT, whatever you want to consider here goes into the cloud. We really need to start bringing the cloud to the edge as we move forward. So a little bit about what we do, and what we're really focused on is that we're an optical sensor company. So what we are focusing on is measuring current, voltage, vibration, and temperature optically. All of our sensors are optically isolated from the grid. So what does that mean is that we're literally using optical components to measure electrical fields or magnetic fields. We've been doing this for quite a while now. So we were founded in 2011, and we're really leading the way to get optical sensing deployed in the grid. Some of the attributes of optical sensing that is, I think, beneficial is the fact that you are now isolated from your measurement. What does that mean? It means that you can actually, high transients, fault conditions do not actually translate down to the pole or down to the measurement device. So it gives a higher level of safety. The other great thing is we're not a source of sparking or fire. By being isolated from this, it gives us a lot of important attributes. The other thing that's interesting too is we're really digitizing sensing. If you think about a lot of the sensing now, there's two main types. You have your traditional CTs and PTs, and you have self-powered bird on the wire that are digitally connected. What we've really done is we've taken a solution that's much more modular, and we've taken a process that allows for mass deployment and actually enable overall ownership and deployment costs to be much lower because we've standardized a modular platform. We've worked with some major customers from throughout New York State, throughout the country, and we're pretty excited about some of the deployments we've done and where we're positioning. So we have a complete platform, and our platform is a little bit different than most sensing platforms, and the fact that we're modular and we use a single sensor for multiple voltage classes. So for example, traditionally, if you're using a CT or PT grid sensor, you'd have one for 25 kV, you have one for 15, you have one for 12.5, 8, you name it. Each sensor would be different for each voltage class. When you switch to optical, you have one sensor for all voltage classes. For distribution, they step up to sub-transmission, and now you can have one sensor that measures from 4 kV to 38 kV, and you don't need to switch them out. All of our sensors are actually modular, so they all use what we call the M410. The M410B is a grid processor that you're actually able to measure any one of our sensors, of the various sensor types we have. We have overhead, which are hanging. We have the line post, which you can see here, all the way up to 72 kV. In addition to being optical, it gives us the benefit of that we can actually put safe sensing into vaults and underground applications. I've talked to many optical solution is that many of our utilities, people actually in the trenches, people actually in the vaults, they like the fact that by having something that's isolated for the measurement gives them the capability to make sure that, yes, when they go in the vault, that there's actually no voltage and current being applied, or it's totally shut down. But the second thing is they're not nervous about the fact that we are conductive, we're non-conductive. So it gives that second level of being able to put sensing where traditionally it's been difficult or challenging. Really, let's talk about how it works, because it's a question I get quite a bit, is how can you actually measure electrons using photons? So we use two different methodologies here. We use something called Pockels effect and Faraday. Pockels effect is essentially when you take an electro-optical crystal and you apply it to a field, it changes the phase of the light. So by actually putting together the system that we have is that we're able to measure not only the electrical field, but the phase angles, frequencies, and harmonics all in one. And additionally, we measure DC offset, and you're able to give a multi-pronged measurement using a single sensor in multiple voltage classes. Likewise, in the current side, is we use something called Faraday rotation. While this isn't new to the industry, there's been many providers that provided optical current sensors. What really makes us different is the fact that we're not fiber optic based. So what does that mean? What it means is it's much easier to deploy and actually install than typical fiber base that you cannot break the fiber. We use something called polarization to measure our current, and that's both able to measure AC current, DC current, harmonic phase. And between the voltage and current, we can provide the K-bar, all the power measurements, and the phase-to-phase, phase-to-neutral measurements across it. We do have other technologies, but primarily today what I'll be focusing on and talking about is what we can do for the grid. Each one of our sensors has a temperature sensor in it. We do that for multiple reasons. And the interesting thing is this gives us the opportunity for future deployments to actually add temperature and temperature monitoring as we progress our product line and work on our product roadmap. But really what we're trying to do is build a system to really fill in this gap, because really if you think what the gap is three things. We need to have more insight. So what do I mean by insight? It's your fidelity of data. The second thing we need to have is a higher order of harmonics measurement. That's incredibly important. The third thing is we need to have future proofing. You know, there's many companies out there like Oracle and I want to say Itron and the Googles out there that are putting this massive cloud-based AI intelligence out there. And really what we need is we need hardware that can help bridge that gap between the actual IoT on the edge and pushing the cloud to that edge. Really where we're going is we're starting to integrate the level of reactivity and predictive analysis so that you know what fault's happening before it happens. We're all familiar with Blizzard and the fault identification, but really where we need to go, the grid of the future, is we can't afford to have assets break down. We can't afford to have predictive analysis of where crews and equipment need to be deployed. So that's really where we're heading. But to do this, step one is you have to have an easy way to get sensing that can give you the data you need. It's really the first step. So what I was talking about is the ghost in the machine here, the harmonics. And I'm sure that a lot of the IEEE conversations, a lot of the talks that I go to, a lot of the conversations I have is harmonics up to the 250th, but going even into hyper harmonics. You know, these nonlinear loads that we're applying because they're so energy efficient, such as LED lights, computers, phones, chargers, all these nonlinear loads are adding more and more harmonic content to the grid. And it causes multiple problems, right? Equipment overheating, cables, loss in energy, loss in efficiency of transmission of energy, and it can actually be exacerbated to create more harmonics as equipment fails. And this can actually lead out to false tripping and imbalance. I was actually talking to a friend of mine who's a utility engineer, and they can actually detect when the harmonics loads are so bad that they're overloading phases versus others. And this is becoming more and more of a problem as these nonlinear loads go online. And I think we're going to see a lot more of that. So to kind of summarize a little bit more, and I want to get through this so we can have more of an open discussion, is that if you think about some of where we're heading is there's a fundamental shift to going to the customer-centric grid, bi-directional flow of energy. To me, that's exciting. I know for utilities that can be challenging, but I think there's a big opportunity here for us to really hone in on these challenges and build this grid that's more, I want to say, reliable. It has a better controllability of the bidirectional flow, and it's enabling customers, right? Now, I know there's many debates about how does this affect rate cases, and how does this actually, how do utilities capitalize on this as we go more and more into a customer-centric grid? But the grid's going to have to be there nonetheless to transport the power. I think what we have to do as innovators, as operators, as the people at the end of the day that keep the lights on, is we really need to focus in and grasp these challenges. And no single company, no single utility is going to have the complete solution. Really, what we need to do is there's going to be many partnerships here between both industry and utilities to make this happen, right? And that's what we're seeing quite a bit of. We have many commercial partners, while on the outside may look like we're in competition, but no, we can actually add joint value to the customers as we develop more intelligent solutions. So I like this chart because what it does is it really summarizes some of the requirements that are changing, right? And what does this mean and why do we need better sensing, right? Is that revenue grade measurement is becoming more and more important. We have solutions for that. That's not a problem. What we don't have a solution for is mass deployment, low cost overhead, and low cost revenue grade as we have more prosumers and commercial generator consumers coming online. Voltage regulation and protection is much more important also. As we put more power on the grid, to make sure that we have high power qualities, we have to make sure that the voltage is correct and obviously well balanced, not only between phases, but actually how well balanced it is within the actual inverters and conversion of the DC to AC. So DER awareness is huge, right? The more and more points we tie in, it goes back to the point about harmonics. We need sensors that can measure harmonics, right? Now, one of the things that gets skipped is that it has to be mass deployable. It has to be something that's self-commissioning. It has to be something that's modular. It has to be something that ties into your existing assets. For example, if you have a switch bank, a cap bank controller, you have to be able to tie into that. So the sensors of the future and the sensors of what we've really focused on is keeping it modular and keeping them low cost per data point. Really what we need to be able to provide to our utility customers is a power quality point that can also act as an edge device that can also control a local device all in one. And that's really where it's heading to. Situational awareness. This is an interesting topic, and I know we only have 40 minutes to talk about it, but situational awareness is fundamentally changing. The fact that if you really think about how we're going to have to start to react is that the edge device is going to have to make intelligent decisions that it reports back to the cloud, and the cloud as an AI device will report back into the control room, with ultimately the operator having final say. But in protection and emergency situations and where fire could start, that needs to be pushed on the edge so it happens in near real time. We're talking within wave cycles or half a wave cycles at protection level on the distribution grid. So that's very important. To do that, it's two things. It's digital edge intelligence. And then last thing is safety. Safety is the number one factor, not only for the people actually having to work with equipment, but also for prevention of fires and other catastrophic events that could potentially happen. So we make sure that we're really isolated from this. So let's paint the picture of what this really looks like in the grid of the future, right? So we've driven this this is very simplistic, but it's very, it's a good illustration of where we're heading, is that we're having now microgrids tie into the larger grid. We're having wind farms tie into solar farms. We're having residential areas that have to be well balanced. And then we put all this into places that require high reliability and high uptime. So the grid of the future is going to have multiple points of these measurements that have to be interconnected and act as a intelligence that has to come back and localized at a swarm level or at a level that's contained within criticalities of diagrams like this, where it can actually be controlled. So let's just talk a little bit about, and then we'll get into the next slides here is, so to really achieve this, it's not one sensor, like I said before, it's multiple sensor types, and it's sensors that need to be both overhead, underground, in substations. So you need to understand what's happening at the substation, you need to be able to understand what's happening at the wind farm, the microgrids, the battery storage, and there's multiple sensor types required to achieve this integration that we're creating, right? So really what we try to do is, with our solution, is we've tied this into multiple sensor types for underground, overhead, and substations so you can deploy Currently, we use DMP3, which is a pretty common platform that we use to actually help control. Now, this goes in typically to ADMS, DMS, OMS, and SCADA all stacked up into the centralized operations. But what our technology really enables is not only this, but is in the future when a lot of this centralized operation is actually embedded onto our system at an AI level and a cloud level. That's the exciting part as we progress. But the first steps are, I'd like to show you guys a couple of use cases, and maybe we can stop it and have more of an open dialogue and really get some good questions in. So first thing I talked about is the challenge of underground sensing. One of the sensors that we have is what we call the underground elbow sensor, and essentially it's a universal sensor that plugs into elastomode, into multiple elbow types, and it can actually be placed on the back of a dead brake into your device. Now, this has been a challenge because a lot of concerns around two things is it has to be reliable, robust, 100% waterproof, right, and submersion rated, and it also has to be dielectrically isolated, yet provide power quality measurements. So we've came up with this product and we've deployed this with some of our customers, and it's been pretty exciting to see that, you know, we can retrofit on an apparatus that's 50 plus years old. So from the utilities perspective is it's leveraging an existing asset and increasing its value while adding power quality and localized control. Once again, volt VAR is a very important thing, and this is another application of where we used our sensors. You know, line post sensors are typically a CT or PT, right? Doesn't give you that full potential of the measurements you can get. So we've deployed this solution here, which enables us to actually replace existing line post sensors or even insulators to drop in as a solution. Now, this particular solution is not only giving a power quality measurement, it's also controlling a cat bank as needed based on the voltages it's measuring and reporting back. An installation like this, approximately 2 hours for a well-trained crew, and this is something that we're seeing quite a bit of installation around. Once again, by having a modular solution, it gives you flexibility of having multiple sensor types in the substation. For this particular customer of ours, they're building out a substation, but they didn't want to have to go through all the rework, all the framing to add in traditional line posts or CTs. They're able to use one of our sensors and mount them on existing assets and hardware to get the power quality measurements for the different feeders and points of interest.